G'day. This is a quick look at the MPLab IDE along with Microchip Code Configurator at using PIC devices as logic devices, basically ignoring the inbuilt CPU. So I'll open up the Code Configurator here under Embedded. And you can see the device I've chosen for this project is the PIC16F1713. There's a nice chip in terms of its peripherals, but the CPU in it is very minimal. It has very little flash, very little RAM, etc., which for our purposes is absolutely fine. Internal oscillator configuration here opens by default. You probably want to be using the internal oscillator, not using an external crystal, because there's no point. And you can turn this all the way down to the low frequency oscillator at 31 kilohertz. In this state, the chip itself is very, very low power, a couple of dozen microamps. I'm not sure on the exact figure for this part, but very, very low. So it's nice to not use up much resources. In many cases, with the number of chips that this part can replace, it may be even more power efficient than discrete digital logic, which is just sort of a nice bonus. In this mode, you basically only need power and ground into the part for it to operate. The only outlier there is the M-clear pin, the master clear. This operates as a reset pin, so it does need to be pulled up or down depending on whether you want the chip to be in reset. What you can do is in the registers tab here, there is an M-clear enable bit. So now you can change that if you disable LVP first. So now the M-clear function is digital input. It does require low voltage programming to be disabled as well, which is this one, but that's fine, we're not using that either. Now you can see the M-clear pin has changed to RE3, which means we don't need a constant signal on that. We don't need to pull that up or down to keep the chip out of reset. It will just work. Just give it power and ground. Now, when programming this chip, you do still use that M-clear pin, the RE3 pin, but your program will actually apply a higher voltage. It's about 12 or 13 volts to that pin, and that will override the internal digital logic state and force the chip into a programming mode. It's called high voltage programming. So as long as you have a proper programming device like a PIC kit, then you won't have any problems there. Okay, so that's the basic configuration for the chip out of the way. The first peripheral I want to look at is the configurable logic cell. So you can see this chip has 4 configurable logic cells, and this is the basic interface for it. If I zoom in on here, we have 4 software-defined inputs and 1 output. Now I'll go through and set up these inputs first. We've got CLC in 0 here. We set this to input 1, input 2, and input 3. Now there are a variety of other inputs you can use here. We've got the outputs of the comparators, the outputs of timers, the outputs of a PWM driver. You can directly drive it from the serial peripheral, timer, overflows and matches, the TX from the software serial port, zero crossing detector, etc., etc. It's very sort of liberal in where you can get your inputs from. This list also changes depending on what pin you're looking at least in most devices. So there will be some differences in this list depending on whether you're looking at the first, second, third or fourth input. So now we're using these generic CLC inputs. If you have a look down here at the pin manager, we have the CLC input 0, 1, 2, 3, and across this matrix you can choose what pin you want to map those to. So for instance, I can move that over here. So now on port C, we have CLC in 0, 1, 2, and 3 mapped to pins 0, 1, 2, 1, 2, 1, 2, 1, 2, 1, 2, 1, 2, 1, 2, 1, 2, 1, 2, 1, 2, 1, 2, 1, 2, 1, 2, 1, 2, 1, 2, 1, 2, 1, 2, 1, 2, 1, 2, 1, 2, 1, 2, 1, 2, 1, 2, 1, 2, 1, 2, 1, 2, 1, 2, 1, 2, 1, 2, 1, 2, 1, 2, 1, 2, 1, 2, 1, 2, 1, 2, 1, 2, 1, 2, 1, 2, 1, 2, 1, 2, 1, 2, 1, 2, 1, 2, 1, 2, 1, 2, 1, 2, 1, 2, 1, 2, 1, 2, 1, 2, 1, 2, 1, 2, 1, 2, 1, 2, 1, 2, 1, 2, 1, 2, 1, 2, 1, 2, 1, 2, 1, 2, 1, 2, 1, 2, 1, 2, where those pins will be laid out. So nice and easy to see how the device is going to work after you've set it up in this system. Now, for each of these logic gates, you can see there's the crosses on the wires feeding into a logic gate. So you can click that and connect the wire through. And so you can go through and connect different signals into different gates to mix what you want. If you don't want to use a gate, that's fine. Don't use it, just don't connect anything to it. You can also click these lines again to make them an inverted signal. So you can go through and invert certain signals and not others when they feed into the initial stage of gates here. The output of this gate can then be inverted or not. Feeds through a bunch more gates to mux it down into one signal. Finally you get a buffer at the end which you can invert or not. So this is a standard AND OR gate chain, but there are a variety of different modes you can put the SR latch into. So you can, for instance, use an SR latch, which gives you your set, reset, latching behavior. And so you can use any of these 8 inputs here, going through an OR gate into the set pin, or any of these 8 inputs here, going through OR gates into the reset pin. And you can invert signals as desired. Again, there's OR and exclusive OR. There's a D flip-flop with a latch enable. Again, basic D flip-flop, so toggle on and off. There's a 4-input AND gate. And yeah, JK flip-flop. Lots of different basic layouts for your digital parts, and you can go through, and a lot of these, like, although there are 8 gates on the screen here, if you only want to use one, that's all you have to use, because if you have no signals going to any of the other gates, then all these 3 will effectively be inert, which means this gate won't be doing anything, it'll just be passing that signal straight through. This gate won't be doing anything, this gate will just be passing that signal through, and so will this one. So you can effectively ignore everything there apart from the gate labelled 1 if that's all you want to use from this CLC peripheral. So very, very powerful and configurable parts, and this chip has 4 of them. Now the output of this, again down in the pin matrix you can see CLC1, output, you can choose to output that onto, we'll use port C4. So again, you can see it on the pin diagram up there, see where it's outputting. Now, one trick you can use as well, if you're using multiple CLCs, the inputs of this CLC may not include the output of the previous CLC. C1 out and C2 out aren't it, they're from the comparator. So CLC1 out and CLC2 out are not options in this list. But what you can do is select an unused CLC input, so in this case we're looking at 3, and now I can actually remap this CLC3 to be on the same pin as the output. So now when the first CLC gate outputs a signal, it will output it to that pin, and that will work as an input into this CLC module. So using that you can chain the CLC modules together if for some reason you need more gates than they actually provide, or you want to make more complex digital logic. The disadvantage of this is that it does occupy an I/O pin. The advantage of this is that you do actually get a point to probe into the internals. You can see what the signal is when it's passing between the CLC modules by probing that pin. So it's both good and bad, but in a device like this where we're basically just using it for digital logic, it's not really a big limitation. So yeah, rather cool. Other peripherals I'll quickly go through here. We have the comparators. So you can see it's automatically set up the comparator 1 here. We've got input pins, we've got the plus and minus inputs, mapped to various pins. The CLC in C1 in X means that it's for possibly multiple other operations. It's not just in 0 or in 1. That's in here. You can have in 0, 1, 2, 3 all on the negative side. Now, these can be remapped at runtime, which is why they have multiple, sort of like the CN0 plus and CN1 plus, even though this is all in C1. Now, you can also use, for either of the positive or negative inputs, you can use the VSS or VCC rails, VSS. There are 2 internal DACs that you can use, and there is a fixed voltage reference, which is what you'll most commonly use for these parts. The fixed voltage reference part internally outputs a 1.024 volt reference. You can then choose to multiply it by 2 or 4 to give you a 2.048 volt or 4.096 volt reference. And yeah, it can have different amounts of gains to the analog to digital converter versus to the comparators and other sensors. So that lets you define your threshold for the comparator in software. So you can say, bang, there, 4.096 volts. This one will have the positive input as CN0 and the negative input as fixed voltage reference. So now we have a basic threshold detector. When the positive input is above the fixed voltage reference, the output will be high. When it falls below, the output will go low. And you can invert that behavior. There is a low power mode for the comparators, which will it slows them down, but makes them use a lot less power. I generally don't bother with that because they draw quite little power anyway, but if you're working on a battery operated application or such, then yeah, it can be nice. Especially in terms of what we're talking about here, where we're using the hardware peripherals without leveraging the CPU. You can put the CPU in sleep, and this whole part can be extremely low power, which means with the logic cells you can use them for some very basic smarts to your device even while it's off. So that's a simple way to sort of more intelligently decide whether you need to wake up the CPU in a certain situation, or if you want to still provide manual control over some feature even without turning the device on properly. Or in many applications you may never need to turn the CPU on, so you're only using these logic functions. So it can be quite helpful. So that'll do for the comparator. There is also op amps. You have 2 fast, high bandwidth rail-to-rail op amps. So they're very, very useful for both to buffer the internal DACs, so you can get some decent current out of the internal DAC, but also to utilize for being a generic op amp. There is a tick box here for unity gain configuration, where you can see down here we have the op amp plus, minus and output mapped to pins. So in this configuration it is just a regular op amp. You've got your 3 pins there, nothing else in the system will really interact with it, it's just a hardware op amp exposed to those 3 pins, powered from VSS and VDD. You can use unity gain configuration, which will actually deselect the negative input. So now it is just a simple buffer. Whatever voltage you put in on the plus input, you'll get out on the output, but decoupled. So again, very powerful, just simplifies a lot of work. You can cut out a decent chunk of your circuit by utilizing these 2 op amp modules and not needing discrete circuitry to handle it. One of the last ones that I'll look at is the numerically controlled oscillator. This one obviously will only work if your internal oscillator is running at high speed, so a little bit higher power mode. But you can define what frequency you want it to output in very, very tight steps. So it's very sort of, you'd use this for a variety of, I don't want to say VFD because it's far too fast for that, but if you're talking about other digital circuits on a board, then having an arbitrary clock that you can adjust in 1 kilohertz increments is pretty useful, to be able to tune your logic or what have you. So you can just use this as a generic clock generator. And once again, it just has an output that you can map to any pin. Well, anything in port A or C. Is there anything else I would like to go over here? There's a zero crossing detector. Very, very simple. Just input on it and feed an AC waveform to it. If the waveform is going to be higher peak than VDD or VSS, then you should use a series resistor, but it can tolerate input resistance of up to at least a megohm, probably a bit more, which means you can even use it with mains. So you can put like a 10 meg resistor between mains and this pin and just directly sense mains voltage to find the zero crossing point. Now that's not necessarily advisable because you're breaking isolation, but if this chip is something that's going inside a sealed mains powered unit, then that can be very, very useful and saves you going through a whole bunch of steps with opto isolators and whatnot when you don't actually need isolation anyway. Can also be used with audio to determine the input frequency. Of course, that's like, it works with tones. It's not so good with complex music, but yeah, still handy little peripheral. Normally you can just use a digital input for zero crossing detection, but then you'll have the pin logic threshold voltage, which is usually around 2 volts. So if you're looking at, say, 12 volts AC, and you have your pin logic threshold of 2 volts, you'll find that the positive going part of the AC wave, you'll have a zero crossing sort of closer together for the positive going part, and then it'll be further apart for the negative going part, because you've got that 2 volt offset in what you're counting as zero crossing. Whereas this will actually detect 0. So for bipolar signals, it's very, very handy to have a peripheral there to just sort that out for you. Complementary output generator. Now this is, I won't delve into this, I'm just sort of showing it exists. This is useful for PWM. So you can define a PWM output here and then use a complementary output generator to give you a opposing output with optional deadband or phase delay or a variety of other things. Very useful in motor control or even in an inverter design, that sort of thing, to reduce that shoot through, where if you turn the high side, if the high side gate's on and the low side gate's off and you want to swap their states, if you do that at the same time, due to line capacitance and whatnot, there will be a short period where both gates are actually on, and that will give you shoot through, where your supply voltage will shoot directly through your high side and low side output switches. Using the complementary output generator, you can use one PWM signal to drive both gates and provide a deadband between them, so that there will be a time when both gates are off before transitioning to one being on. So that then prevents shoot through and other nasty side effects, as well as you can do blanking and phase delay, and it's a very complex sort of beast, but again, can be useful if you are in a situation that you need something like that. Then there's it's often quite a hard sort of bridge to jump if you don't have a peripheral like this, which very few other microcontrollers seem to provide unless they're specifically designed for switching applications, whereas this is just a generic logic part. And again, you've got a DAC up to an 8-bit DAC. You can define this at configuration time and just say, I always want you to output a specific reference voltage, and then you can utilize that in the op amp or the comparator or such. And so you've got an 8-bit DAC and a 5-bit DAC, as well as the 2-bit internal fixed voltage reference, which I believe you can select as a positive reference here. And then you can also buffer these through the op amp if you want to be able to drive loads at 20-25 milliamps, something like that. So yeah, extremely versatile chip. Obviously I've been very brief going over things here. You could spend a long time going through this chip. I highly recommend reading up on the datasheet. Now there are a lot of chips that have these peripherals. This was just a particularly nice combination that has a lot of the sort of nice peripherals while having a very basic and minimal CPU, which means that it's a fairly inexpensive chip. So nice one to dive into and have a play around with. Microchip are one of the few companies out there that will send out free samples to students and even hobbyists. Please don't lie on sample application forms. A lot of the reason why, like in industry, if you go to request a sample and you get rejected from someone, then you have to go through your company's purchasing department and justify why you need that chip and how you're going to use it. A lot of the time you're not willing to throw down on that chip yet, you're just asking for a sample so you can check it out. And people sort of abusing sample programming programs and going in there and saying, hey, yeah, I'm a big business, I need these chips to test with. Companies get swamped with millions of sample orders, and it's just not cost effective for them to continue that program running. So hobbyists sort of lying on these sample forms will actually hurt people in industry. So yeah, please do not do that. But Microchip are one of the few companies that you can go to them and literally say, like, I like Arduinos, heard your chips are good, please give me some. And they will. They'll just, send you through a few, instantly sample account approved. You can order 3 different types of chips and 3 of each chip. I think the first time you place a sample order you have to pay postage, but after that they'll even pay the postage for you. So it's a very, very good program. Just please don't abuse it. Again, Microchip are one of the few companies left that still have an open sample program like that. So if you want to grab a couple of chips to play around with and see if Microchip parts are something that you want to use in future, then by all means do it. Just please don't slam them with orders and use the sample program as the only way that you source Microchip parts, because that will ruin it for the rest of us. But I hope you enjoyed this quick sort of look through what these PIC chips can do, and I'll be making future videos, so please remember to like and subscribe. See you next time.